Hello, this is Kevin, and this is a brief overview of my answers to the final project for Data 605. We're given two problems. The first problem is relating to probabilities, and we're asked to generate 10,000 draws of the random variables x and y. I chose n equals 41 for the range of numbers from 1 to 41. For the variable x, and for the variable y, that's normally distributed with a mean and standard deviation equal to 21. In terms of the distribution, the variable x follows a uniform distribution that looks like this. The variable y, on the other hand, follows a normal distribution centered around 21. And little x and little y are given by the dashed lines in blue. Little x is the median of the random variable capital X, and so the median of that distribution is approximately 21. For y, little y is given as the 25th percentile of the sample distribution for capital Y, and that comes out to approximately 6, as we can see here. And we can compute those both in terms of the sample distribution as well as in terms of the actual theoretical distribution. So again, little x is approximately 21, little y is approximately 6.8. So in part A, we're asked to calculate the probabilities. The first probability is a probability of the random variable x being greater than small x, conditional on x being greater than small y. This is a conditional probability, which we can express mathematically through the usual formula. Working through the math, that ends up being approximately 58.5%. The next probability is the joint probability that x is greater than little x and y is greater than little y. We can either assume that the variables are independent to calculate this, which we'll see whether or not that's a good assumption further on in this problem, or we can just measure it from the sample numbers that were generated. In either case, the probability comes out to approximately 37.5%. The next section is the probability of x being less than little x, conditional on x being greater than little y. Again, we can compute this conditional probability based on the usual mathematical expression, and both from the actual distribution as well as the sample distribution, this comes out to approximately 41.5%. Alternatively, as a shortcut, if you realize that the probability in part C is just the complement of the probability in part A, you can relate these more simply as the probability is just 1 minus the probability from part A. So this table here summarizes the various probabilities, both from the sample distribution as well as from the actual theoretical distribution. The next part, part B, we're asked to investigate whether the joint probabilities equal the product of the individual probabilities. In other words, to see whether x and y are independent. So we do that by creating a contingency table, which is what we see here. This just records, in terms of the number of observations, the observations of x and y, the paired observations where y is less than or equal to little y or greater than y, going across the top, the horizontal axis, or on the vertical axis, x being less than or equal to little x or greater than little x. We can also convert that to probabilities, and what we see is that the joint probability of x being greater than little x and y being greater than little y is approximately 37.5%, which is just what you would expect if x and y were independent. Alternatively, you can arrive at a similar conclusion by looking at the conditional probabilities and comparing that to the marginal probabilities. And there again, you get the result that you would expect in the event that x and y are independent. Part C, we're asked to use Fisher's exact test and the chi-squared test to see if independence holds. And in either case, using the usual hypothesis testing, where the null hypothesis assumes that they're independent versus the alternative hypothesis in which they are dependent, we see that the results of both Fisher's exact test and the chi-square test result in p-values which imply that there is no reason to believe that x and y are dependent, so instead we assume that they are independent. The difference between the two tests are that the Fisher's exact test, as the name implies, can be computed exactly, which depends on using the hypergeometric function. It's valid when the marginal totals for the rows and columns in the contingency table are held fixed. In contrast, the chi-squared test is valid only as an approximation, and that approximation is valid for large sample sizes and for frequency counts greater than 5 to 10 in each solver table. In either case, the results are very similar in terms of the p-values, since the sample size in our case of 10,000 is extremely large for convergence of the two test results. That was problem 1. The next problem, problem 2, relates to the Ames housing data set. And we start out by loading the data and viewing it, and then we provide some univariate statistics and summary statistics and plots for the training data set. We can first get a view of the data by summarizing each of the variables and then plotting some histograms. It's worth noting that our target variable here, sale price, is skewed to the right. And in fact, if you log transform it, you see that it's approximately normally distributed. And the same goes for the gross living area variable. We plot some bivariate scatter plots to see what some of the relationships are for some of the variables in the data set. In this case, we're looking at bivariates among sale price, gross living area, and the lot area, and we see some clear relationships, particularly between sale price and gross living area. We also show bivariates of overall quality and condition, and one of the key variables that we'll end up using is the overall quality, given that it has again a clear relationship with sale price. And we also look at year built and year remodeled. Next, we look at some box plots of the sale price variable by selected groupings of other variables. In this graph, we see the sale price versus neighborhood, and as you would expect, neighborhood plays a key role in determining sale price. Certain neighborhoods are more expensive or more highly valued than other neighborhoods. We also see the sale price versus overall quality relationship, which has a clear pattern. Higher quality properties command higher prices. We also see relationships by building type, house style, the number of baths, full baths and total baths, bedrooms above grade, total rooms above grade, as well as year sold and month sold. The year sold variable does not seem to be determinative in this case, whereas a month sold, perhaps there might be some seasonality patterns. And finally, the last few that I'll mention are sale type and sale condition, as well as roof material, which roof material might be an indicator of how recently the home was renovated or the roof was replaced, which might factor into the sales price. The result of all this is to get a short list of predictor variables that we can use in the regression below. The next part of the question asks for a scatter plot matrix of at least 2 of the independent variables. We'll start out by looking at sale price versus gross living area. As you would expect, there seems to be an approximately linear relationship there, which I think is consistent with the idea that one of the common metrics in the real estate industry is price per square foot, and that's something that we'll build on when we look at our multiple regression model. We also look at this relationship broken out by overall quality. The lines indicate the best fit line, whose slope is going to give us the price per square foot. And as you would expect, higher quality properties will have a higher price per square foot metric. We also see a similar relationship by neighborhood, where certain neighborhoods like No Ridge and No Ridge Heights have a very steep linear relationship, implying higher valuations compared to other neighborhoods. We also see a similar relationship by housing style. We also looked at sale price versus lot area. That relationship was not as clear cut, but it's worth looking at in any case. In the next part of the question, we're asked to derive a correlation matrix for any three quantitative variables. In this case, I chose lot area, gross living area, and sale price. Here we can see that lot size and gross living area has approximately 26% correlation. Similarly with lot size and price, 26%. But gross living area and price are more highly correlated, almost 71% correlation. Next, we're asked to test the hypothesis that the correlations are 0 and provide an 80% confidence interval. Here, the test statistic is given by this quantity. And what we do is we compute this for different pairs in the correlation matrix among lot size, gross living area, and sale price. Turns out that R has a correlation test function, so we can more easily use that rather than computing the test statistic by hand. I only realized that after computing it by hand, but in any case, we can use that to confirm our results. The p-values, as it turns out, are very, very close to 0, which allows us to reject the null hypothesis and conclude that the pairwise correlations indicate that the population correlations are not equal to 0. And furthermore, the 80% confidence intervals from the correlation test function in R can be arrived at with these confidence intervals as shown here. In the next section, we're asked to discuss the meaning of the analysis and whether there's family-wise error. What we've done is we've established that the sample correlation estimates suggest that the true population correlations are non-zero at a 5% level of significance. And we've also computed 80% confidence intervals. In terms of family-wise error, it's something to think about whenever you're doing a series of hypothesis tests, particularly if they're related on a similar data set. However, in this case, it should not be an issue given that the p-values for the hypothesis tests were extremely small. Even if we were to apply a correction, say for instance the Bonferroni connection, the results of our analysis would be that these correlations are still significantly greater than 0. The next section of the question asks for an inversion of the correlation matrix above. We use R to invert the correlation matrix to arrive at the precision matrix. Next, we multiply the correlation matrix by the precision matrix, and vice versa. In both cases, we get the identity matrix approximately with small errors. In the next section, we're asked to do a LU decomposition on the correlation matrix. I ended up using the decomposition function that we wrote in an earlier homework assignment from week 2. Using that, I arrive at the lower and upper triangular matrices. And once we multiply those together, we arrive at the same matrix that we started out with, namely the correlation matrix. In the next section, we're asked to compute, we're asked to select a variable that's skewed to the right. I chose the target variable sale price, which as we saw earlier is skewed to the right and seems to follow a log normal distribution. We then are asked to use the mass package and use the fit distribution to fit an exponential. I did that, and the optimal value of lambda for the exponential distribution is approximately 5.5 times 10 to the minus 6. I then generated a histogram from the fitted distribution and compared that to the histogram of the sale price variable. And that's what you see in this graphic. The sample distribution is on the left, whereas the empirical sale price variable distribution is on the right. What we see is that the exponential distribution does not closely fit the empirical data. It seems to be missing the hump that occurs near the mode of the distribution, which is approximately 180,000. And it also, the exponential distribution continues to increase as you approach 0. So I also investigated looking at a log normal distribution for the sale price using the same fit distribution function from the mass package. And once we generate sample distribution and also fit the log normal to the empirical distribution, we see that it fits the data much better. That's what we see in this graphic. Next, we're asked to compute the 5th and 95th percentiles from the distribution, which are shown in this table. And again, what we'll see is that the 5th and 95th percentiles are much better approximated by the log normal distribution. From the empirical distribution, for instance, we see that the 5th percentile is 88,000, and the log normal gives us approximately 86, which is very close, whereas the exponential gives us a number about 10,000, which is way off from the empirical distribution. Next, we're asked to compute a 95 percentile confidence interval for the mean home sale price. We do that using a z-score as well as a t-statistic. In either case, the answers are very similar, given that the sample size of 1,460 observations is very large. So the results from using the t-value or the z-scores are very, very close, and we end up with a 95% confidence interval of roughly 180,000 plus or minus 4,000. And finally, it's worth noting that the concept of the confidence interval is different from the notion of the 5th and 95th percentiles. The 5th and 95th percentiles simply indicate what portion of the distribution is below the indicated values, whereas the 95% confidence interval gives you a range of where the true mean is from the population. In the next section, the final section, we do a modeling exercise by building a multiple regression model for the Ames housing price data. If we go back to part A above, we had a short list of potential regressor variables to use, which is this. We end up using that short list to arrive at some key variables to use in the model. I applied a version of forward selection by starting out with some of the key variables and then selectively adding variables one by one going forward. So the base model starting out was a sale price versus gross living area segmented by neighborhood, as well as an adjustment for overall quality. Here the rationale was quite simple. It was to arrive at a pricing metric per square foot, where the pricing metric is differentiated by neighborhood, and then to apply an adjustment based on the overall quality of the house. That base model has a surprisingly good R-squared of roughly 84% using only 3 variables. In model 1, I added house style. That increased the R-squared to approximately 85%. Model 2, I added the roofing material variable, which increased the R-squared to approximately 86%. And then in the final model, model 3, I added sale condition to the model, and that increased the R-squared to approximately 87%. Now, the way I chose those variables starting from the base model was to individually add each one of the variables in the short list and adding them one by one to see what the impact is on the R-squared, the adjusted R-squared. And in each one of those iterations, I added the variable that increased the R-squared the most. So starting from model 0, I added house style. From model 1, I added roofing material. And then from model 2, I added sale condition. I stopped at this point because it's clear from the numbers that there's diminishing returns in adding additional variables. And the risk in adding additional variables is that we increase collinearity among the explanatory variables, and we also increase the potential of overfitting to the training data set. So I stopped at that point, and 86% R squared seems like a reasonable number. In the next section, we're asked to provide model summary and results. For each one of the models, I printed out the model summary showing significance tests and p-values for the coefficients, as well as an overall adjusted R squared. There's also an ANOVA table, as well as diagnostic plots. I'll just review the output for Model 3. What we see from Model 3 is that most of the coefficient estimates are significant. In fact, most of them are highly significant. For several of the variable families, some of the individual coefficients may not be significant. For instance, we see here that quality 2 and 3, the coefficients there are not significant, but overall, the overall quality variable family is highly significant. I'll also point out here the F statistic, which gives an indication of the significance of the overall model relationship. That is highly significant. And what we can also see from the ANOVA table is that each family of variables is highly significant with a p-value for the F statistic very, very close to 0. The diagnostic plots below show that the variance of the residuals don't appear to be drastically increasing, but there does seem to be a slight increase for larger fitted values, which potentially is an issue. Also, the normality of the residuals appears good up until the tails of the distribution. Both for larger values and smaller values, it appears that the residuals deviate from normality. So in summary, I think the multiple regression model seems a reasonable model fit to the empirical data, but there are some issues that are worth investigating further to confirm that the assumptions of multiple regression are satisfied, in particular constant variance of the residuals, as well as normal distribution of the residuals. One thing that I didn't have time to do is to test the collinearity of the predictor variables, and one can test that either by looking at variance inflation factors or more closely inspecting a correlation matrix among the various predictor variables. The final scores that the models had were in the 16 to 17% range. One thing that I was slightly surprised at was that the scores increased for adding more variables. I was somewhat concerned that there might be overfitting, but it doesn't seem that that limit was really reached yet, which seems to suggest that one could achieve even better scores by adding more variables. Finally, suggestions for further work. One was to add more variables to see if this improves performance. Another was to explore other functional forms for the regression model. For instance, potentially log transforming the sale price variable since it's skewed to the right, potentially transforming other feature variables to get a more intuitive or more direct relationship with the sale price variable. And another idea is to do a regression rather than doing a regression on the sale price variable, rather to do the regression on the sale price per square foot variable. In other words, change the target variable to sale price per square foot and then predict that variable before multiplying by the square footage to arrive at the total sale price. Potentially that might achieve better results. And then finally, another idea for further work would be to explore other more advanced techniques, such as using generalized linear models or nonlinear models, or even techniques like ridge or lasso regression. That's about it. Thank you very much.